Hello, everybody, and welcome to the 2022 Photonics Spectra Conference. You're joining us right now with Dr. Shelby Ament, a senior optical engineer at Arizona Optical Metrology, or AOM. She received her doctorate from the University of Arizona's Wyant College of Optical Sciences with a specialization in diffractive optics. She has 5 years of experience in the optics industry, designing, fabricating, and using computer-generated holograms to test optics. This ranges from catalog cylinders and A-spheres to meter-class telescope mirrors. Right now at AOM, she designs and certifies computer-generated holograms for customers, and she develops next-generation metrology products. So today, the focus of her session is going to be on those computer-generated holograms, or CGH metrology. She'll talk about applications for improving manufacturing and assembly, and we'll cover alignment features that can be written into the holograms themselves. If you have any questions or comments, go ahead and type them right into the conference chat box. And if you missed part of this talk, that's fine. You can come back later and watch it on demand. So that's all from me. I would like to introduce Dr. Shelby Ament. Welcome.
Thank you for the introduction. Okay. So the topic of my talk today is computer-generated hologram metrology, alignment, challenges, and solutions. So I'll start off by sharing a video of a CGH measurement of a diamond-turned aspheric mirror. And this is an overall solution that takes a matter of seconds to measure. And the reason that this is such a quick measurement process is due to consideration of mounting datums on the test optic. In this case, there's a bevel that's diamond turned into it, along with precision located mounting balls that are actually located very precisely with respect to the CGH pattern. And then the test optic is mounted directly against these mounting balls. And so there's actually no alignment needed in this setup. And then in addition to these physical mounting features, the CGH includes alignment patterns that provide interferograms. So if you look to the right, we've got these two annular interferograms in addition to measuring the optical surface in the middle there. And these help us understand the alignment of the CGH to our interferometer and the alignment of our test optic to our CGH. And so in this presentation, I want to get more deep into the topic of how do we set up measurement solutions that consider alignment so that we can ensure accuracy of our measurement and we can make sure that there aren't any errors induced from misalignment. So I'll start off the talk by giving an overview of what is a CGH surface figure error measurement. After this, I'll talk a little bit about challenges specific to A-spheres and freeform measurements in terms of their alignment. After this, we'll cover reference datums that are used for optical components, how they're used, why they're used, and I'll give some examples of these datums. And then we'll move into how do we mount our test optic so that we can utilize these datums and relate them to alignment features to ensure that our CGH and our test optic are aligned to each other. And then to finish it off, I will discuss several different types of alignment patterns that can be written onto the CGH and work along with these targets to ensure alignment of our test optic. So to start off, a CGH measurement CGH is used to measure freeform and aspheric surfaces. And the way that it's used is as an accessory to a standard interferometer, such as a Fizeau or a Twyman green. These interferometers will put out a collimated or a spherical wavefront, and the CGH is a diffractive optical element that's used to translate this spherical wavefront into an aspherical wavefront that exactly matches the shape of your test optic. Put another way, the CGH takes rays and sends them exactly normal to the optical surface. So a CGH has many benefits. These include high measurement accuracy. The CGH accuracy can be down to 100th wave as a standard and 1,000th wave if we pay very close attention to the details. It's also beneficial in that it's very versatile. A CGH can be used to measure any type of surface. Rotational symmetry is not necessary, so CGHs are becoming more and more common in measuring things like freeform optics. Another benefit to the CGH metrology solution is that it's quick. Once the test optic is aligned to the CGH, you get a full surface measurement in one shot. And finally, the CGH measurement is powerful. The CGH can be fabricated with multiple patterns on that same surface, and those patterns are registered very accurately to each other. And so what we want to do is take advantage of that capability to not only provide the null wavefront that reflects off of your test optic, but also to incorporate some alignment patterns to ensure alignment of the CGH to the interferometer and of your test optic to the CGH. On the right side of this slide, I have here an example of a CGH that was used to measure the two lens camera assembly for the LSST, the Large Synoptic Survey Telescope. And all of these concentric patterns are used to focus on the individual surface of those two lenses and ensure that they're aligned to each other prior to performing a transmitted wavefront error measurement of that system. Okay, so I've talked about the benefits of CGH measurements, but there are some challenges specific to freeform optics when you go to align them in an interferometric test. When you're measuring a sphere in an interferometer and that sphere has a decenter error, you can always perfectly compensate for that decenter with a tilt compensation. But with an A-sphere or a freeform, we no longer have that perfect compensation with those 2 degrees of freedom. So what I'll show here is an example of surface figure error of 3 different freeform prescriptions. And this is the surface figure error when the test optic is misaligned by 0.1 millimeters in X. And you can see here that each of these different prescriptions has wildly different surface figure error induced from that misalignment, and that misalignment signature looks a little bit different for each of these parts. If we were to actually set this up and only have our interferogram as our feedback, we might think that there's a tilt error, or we might try to compensate for this decenter with tilt or clocking. And so what I show below here is the residual surface figure error that you would see if we attempted to compensate for this decenter by tilting and clocking our test optic. And you can see that we can't perfectly compensate for this decenter error, and that the amount that we can compensate also varies wildly depending on the test optic and the measurement geometry. So all of this is to say that we can't really trust using the optical surface itself and the alignment of that optical surface with the surface figure error as our feedback. What we need is some independent check that our test optic is aligned to our CGH, and we need that check to be relevant to datums that are important for our measurement. So as I say here, this residual error can impact the measurement accuracy, and it can also lead to erroneous manufacturing feedback. So we really want to avoid this, and we want to understand our alignment independent of this. So this leads me to the topic of datums. A datum with respect to an optic is used to define a reference geometry. It's used to define a coordinate system and specify a tolerance relative to some feature of interest. A well-defined datum should be something that's large enough that you can physically locate it and use it for measurement of these tolerances. And additionally, a well-defined datum should be related to how the optic will be mounted either during manufacturing, final application, or both. So some examples of commonly used datums for optics include the outer cylinder, which can be used to define a mechanical z-axis for circular parts. We can also, in the case of PCX, spherical lenses, we could define an optical z-axis by finding the center of curvature of both of those surfaces and drawing a line through it. And depending on how that lens is mounted, one of these z-axes may be more relevant than the other. Another commonly used datum is the backplane surface. And so if your optic has a plano back surface, or if it's a mirror with a plano backside, we'll often use this to define a datum. And for freeform optics, it's not really enough to know just the z-axis location and orientation. We also need to know clocking. And so this is an example of a freeform, non-rotationally symmetric mirror. And in addition to the backplane, which helps us define our z-axis, we have an edge flat, which is datum B, and we have a precision pinhole datum C. And these two things help us define our X and our Y axis so that we can quantify clocking error with respect to those. So with our test optics, we want to make sure that we have datums called out that are related to how that optic is being mounted. And then when we go to mount our optic in our test, we want to make contact with those datums. So going back to the freeform optic example, what we have here is what's called a metrology platform, which has precision pinholes that are bored into it. And in the case of this freeform mirror, we've pressed some pins into these pinholes that relate to the pinhole called out in the drawing. So our test optic is mounted with respect to datum C and datum A. The backplane is in direct contact with this platform, and the metrology platform is intended to hold our test optic and at the same time hold alignment targets relative to that test optic. And the idea is that we will design alignment patterns into our CGH that send light onto these targets. And these targets are in a known location relative to the datums of our test optic. So overall, we have the metrology solution for alignment and for measurement of our test optic surface. So this is what the metrology platform looks like in real life with this freeform diamond turn mirror and some of these alignment targets that interface with these alignment patterns in our CGH. And what we did in this demonstration is our precision pinholes are used to hold what are called magnetic nests that have posts. And inside of these magnetic nests, we can hold a variety of targets. We can hold a photogrammetry target, which is a half sphere with a white screen used for visual alignment. We could also swap that out with a tooling ball, which is a reflective metal sphere. And we could swap that out with what's called a sphere-mounted retroreflector, which is a corner cube mounted inside of a sphere. And so all of these things can be interchanged depending on what your alignment pattern is. So I'd like to go into that in a little bit more detail. So next topic will be the different types of alignment patterns that we can design into our CGH. I'll go into these one by one, starting with the most coarse alignment. So when you're initially setting up your test optic, it's really useful to have a coarse alignment aid that's visual. So what we can do is we can design alignment patterns that bring light to focus either as a spot or as a crosshair. And these focal spots or crosshairs need to be centered with respect to a target or maybe even a camera. So the idea here is that you would have your test targets located with respect to your test optic, and you would just move your optic so that those spots are in focus and centered on our target. And we can achieve this to an accuracy of better than a millimeter. Oftentimes 0.1 millimeters is achievable by eye. And this is certainly accurate enough that we can move from a coarse to a fine alignment, and we can start to see fringes on some of our fine alignment patterns. So once we've done our coarse alignment, we can move on to our fine alignment. And one example of this is what's called a cat's eye focus. A cat's eye focus is an alignment pattern that comes to focus directly on the optical surface. It might focus on the vertex of the surface, Or in the case of the example I showed at the beginning of my presentation, this ring is actually a cat's eye ring that focuses on a flat annulus that has been diamond turned into that optic. In either case, what the cat's eye feature allows you to do is get a sense of your focus or your Z alignment of your test optic. And you can use your cat's eye as a coarse alignment if you place a lens tissue against your test optic, bring that light to focus. And then you can remove the lens tissue and use the fringes for a fine alignment of the Z degree of freedom. The next alignment pattern that I'll discuss is also an interferometric pattern, and it's light that is converging onto a tooling ball, a reflective sphere. And so the idea here is that we might have a tooling ball in contact directly with our test optic, or again in a known location on our mount. And the light is meant to focus to the center of that tooling ball, and so it reflects as a confocal reflection off of the tooling ball. And so our goal here is we will see tilt fringes if our tooling ball is decentered, and we will work to minimize those tilt fringes. And then if the tooling ball is too close or too far away axially, you'll also see curvature in those tilt fringes, which indicate power error. And so this is really similar to aligning a sphere in an interferometric setup. So this test works well over distances of a few inches to the tooling ball, but we find that it does suffer from diffraction effects over greater distances. So what we like to do is aim for an F number less than F5 to avoid the effects that I show here on the right. When you have a circular aperture, you'll start to see Fresnel rings over large distances. So this works pretty well, but another difficulty of it is that you have to be in really close alignment before you're able to see fringes. So to improve the ability of aligning our test optic, we came up with a new technique, which is called a line focus reference. And so the line focus reference patterns are similar to the tooling ball patterns, except that instead of focusing the light to a point, we're now focusing it to a line. And what this allows us to do is it allows us to separate the different alignment degrees of freedom. And so misalignment along the direction of the line won't really impact our ability to see our fringes. We're only aligning the degree of freedom that is perpendicular to the line. So in the case of a vertical line, this type of reference pattern is used to align dx. And for a horizontal line, this will allow us to isolate dy. We bring these lines to focus specifically to a sphere-mounted retroreflector or a corner cube. The way that this works is that if our corner cube is misaligned in dx, if we follow that incident ray as it reflects off of the two surfaces of the corner cube, it will appear to us as if the line has actually shifted in the opposite direction by delta x. And what we see on our interferogram are tilt fringes. So the idea here is that we will include multiple line focus references for the horizontal, vertical, as well as DZ and clocking degrees of freedom. And so I'll get into that a little bit later in the presentation. So it helps a lot to actually see what this looks like as an interferogram. So the movie here on the left is showing the process of aligning one of these sphere-mounted retroreflectors using a line focus reference pattern. So the process is really just adjusting that SMR position to minimize the tilt fringes, as you see here. And you'll notice that as we're aligning it, you're starting to see a little bit of a chevron effect in those tilt fringes. And that's because we've actually designed one to two tilt fringes in the opposite direction to increase the precision of this alignment process. So as we go from coarse to fine alignment, you'll see that the fringes, they tilt and then they kind of become parallel to each other. And so what happens is in final alignment, the goal is to get those tilt fringes perfectly parallel to each other. And if we can do this by eye, we can get it aligned to about 1/10 of a fringe, which is equivalent to 3 microns of lateral positioning error. And so this was really done because the eye is a lot more sensitive to tilting of fringes versus just looking at a gray null pattern. So there's a lot of benefits to these line focus reference patterns. As I said before, we've separated the degrees of freedom. This increases the dynamic range because we're now only sensitive to a single degree of freedom for each pattern. And as I said, the chevron arrows indicate not only that you're becoming more aligned, but it also indicates the direction of the alignment. So I'll get into that in more detail here. So I'll show each degree of freedom with some movies to show more detail. So in this case, if the test optic is shifted in the X direction, we'll focus on these 3 patterns. And you'll see that they all point in the same direction, indicating decenter in the X direction. If we want to focus on decenter in the Y direction, we'll focus on just this pattern here. And you'll see that there's more tilt fringes in that pattern as it's misaligned in Y. And here I go in each direction. Next, I'll show you clocking. So for clocking, we have 2 sets of patterns that are measuring dx, but one of these patterns is on the top of the CGH and one is on the bottom. And if there's a clocking error, this shows up as opposite decenter errors on the top pattern compared to the bottom pattern. So if you look at the top patterns here, you'll see that they point to the right, while the pattern on the bottom points to the left. And that's telling us that our test optic is clocked, which is an important degree of freedom for a freeform optic. And then finally, we can use these line focus references to understand error in the Z direction. This is done by designing 2 line focus reference patterns that are on the top and the bottom of the CGH that are both bringing light to focus on a single SMR that's located in the center. And so if our SMR is too close or too far away, this will present as an equal and opposite error in those 2 patterns. And so as we shift our optic too close or too far away, not only are you seeing the power fringes in our null, but you're seeing that these patterns are pointing away from each other or towards each other. And that's telling you that there's a Z error in our alignment. And so I'd like to show you a little bit about the accuracy of these line focus reference patterns in the lateral direction and in the axial direction. And the resolution of this technique depends on the size of the pattern as well as the distance between the CGH and the SMR. But this just gives you some idea that you can get lateral resolution to a handful of microns and axial resolution to the tens of microns range for this type of pattern. Okay, so I've covered the CGH alignment patterns, and I just want to conclude by restating the main points that we've covered. So computer-generated hologram metrology has several benefits, such as 100th wave accuracy and snapshot measurement time. However, alignment of aspheric and freeform parts in a CGH setup is critical because these shapes do not have the perfectly compensating alignment modes that a sphere has. So it's really important to define alignment of your test relative to datum features that are meaningful in terms of how that optic is being mounted, either in the manufacturing process or in the final application. And so if we have datum features in our technical drawings, we can then relate this to how the optic is mounted, and we can write patterns onto our CGH to provide feedback for alignment with respect to those datums. We can mount our test optic in a metrology platform that holds alignment targets, which work in concert with these CGH patterns so that we can provide a full metrology solution. We can provide confidence in your measurement, we can speed up the alignment time, and we can make sure that the measurement is relevant to how the optic is being used in its final application. So if you have any further questions or if you need guidance setting up an alignment plan, please reach out. We would like to partner and help guide you towards a solution that works for you. So thank you for your attention.
Thank you very much, Shelby. I would like to close with a couple of questions for you. And to everyone here right now, if you haven't already, you can type your questions and comments into the conference chat box. So Shelby, how many alignment patterns do you recommend including on a CGH?
It really depends on the shape of your test optic, the symmetry of your test optic, and what degrees of freedom you need to align. So if you have a rotationally symmetric A-sphere, for example, we really don't care so much about clocking, but we care about dx, dy, and dz. And for this, you would need 3 different patterns. For example, a line focus reference for dx, a line focus reference for dy, and perhaps a cat's eye pattern for dz. And for a freeform optic, where you do care about clocking as well as X, Y, and Z, I would recommend 4 patterns, which would basically be the 4 patterns shown here, which allow you to get dx, dy, dz, as well as clocking. So 4 line focus reference patterns for freeform optics.
Thank you. What is the accuracy of a CGH measurement?
Typical accuracy of our CGHs, if you subtract the transmitted wavefront error of the substrate, which is actually our largest error contributor, the accuracy can be down to 100th wave, anywhere from 3 to 6 nanometers RMS. If you include the error of the substrate, that goes up to 20 to 30 nanometers RMS. So we definitely suggest subtracting that error map, which we provide if that error is too large for your measurement.
Thank you. I've got one more for you for now. Where do you purchase SMRs or photogrammetry targets?
You can get them off of a website like Hubs. Hubs sells SMRs, tooling balls, photogrammetry targets, as well as those magnetic nests that you use to hold them.
All right, thanks so much. And thank you everyone in the audience for your questions. And thanks for joining us for computer-generated hologram metrology alignment, challenges and solutions. This is part of the Photonics Spectra Conference, which is hosted by us at Photonics Media. And once more, you've just heard from Dr. Shelby Ament of Arizona Optical Metrology. Thank you so much.
Thank you.